Hello, namaste to all my viewers. Lecture 5 in the seminar series on Clean Water Emerging Frontiers begins in a short while. Thank you for joining us. A very warm welcome to all of you.
Welcome to the seminar series. Thank you for joining the series. These lectures deal with one of the giant problems of the planet, namely water. We had an outstanding lecture on June 29th, the first day of the series, by Professor Rahul Ravindran Nair of University of Manchester on graphenic membranes for water filtration. We had another outstanding individual, Professor Sung-jae Kim from Seoul National University, South Korea, on June 30th, speaking to us on ion concentration polarization. On July 1st, we had Professor Praveen Linga from National University of Singapore, who gave us an excellent lecture on gas hydrates for desalination. Yesterday, we had Professor Thomas Tundat of University at Buffalo speaking on sensors and sensor networks for water. Today, we have two practitioners of advanced membrane technologies. Their work is on aquaporins, the biological water transport channels. An important difference in this presentation compared to the ones we had in the past 4 days is that here is something advanced getting translated to technology right in the field. Mr. Esben Gad is a Vice President for Business Development at Aquaporin. He holds MSc in nanotechnology from Copenhagen University and has worked in international business development for the past 12 years. He is responsible for Aquaporin's commercialization in industrial water, food and beverages, and medical devices. Dr. Jörg Vogel is the Vice President of Technology Development at Aquaporin. He holds a diploma this is called Diplomat, an engineering degree in mechatronics and micro-production technology from the Technical University at Chemnitz, Germany. In addition, he holds a Ph.D. from the Technical University of Denmark. He has been part of the development of Aquaporin Inside technology since 2007. Dr. Vogel is responsible for the R&D groups in Denmark and Singapore, focusing on further development of Aquaporin Inside technology, both in regard to upscaling current membranes, developing new membranes, and their application in the full industrial spectrum. Let me first invite Mr. Esben Gad, followed by Dr. Jörg Vogel, and then again Esben. Over to you, Esben Gad.
Thank you very much, Professor, for the warm welcome, and thank you very much for the invitation to present to you here today. We are very proud and happy to be a part of this series with such excellent speakers, and we hope that you will find our presentation interesting and enlightening. As mentioned, we are much more on the technical and business side of things, having moved on from more pure research. So I hope you will find this interesting. And here we are. I will start out by talking very briefly about who we are as a company, and then Jörg will go deeper into our technology and forward osmosis, which is our current key contribution to the industrial water market and to pure water generally. And then we'll dive deeper into applications in the industrial water market and perhaps also in food and beverages if time allows. Let's see. Yeah.
Okay.
If you want to briefly introduce yourself.
Yeah. So as we were already introduced, I've been in Aquaporin for quite a while, and that's why I'll have experience with the technology and how we came up with putting channels into like our commercial membranes. So if there's any more technical questions afterwards, I will be also happy to take them. But Esben, take it away with introducing the company itself.
Yeah. So very briefly, Aquaporin is a membrane company. We base our technology of using the protein pore called aquaporin from nature and putting that into membranes. So that's our one core technology. We've turned that into two product lines. We do more, you could say, traditional reverse osmosis membranes, and then we do forward osmosis membranes, which is a new and emerging process in water treatment. We have a very strong patent position. We believe in the whole concept of using aquaporins in water filtration. And despite being heavily invested in intellectual property and patents, we pride ourselves of being a very open company. So right from the very beginning in 2005, we have worked a lot with partners and public innovation funding and have taken a lot of students in. We just celebrated our student number 100 graduating, who had been part of Aquaporin. So that's a big part of who we are. We're based in Denmark, but very much with a global outlook, since, of course, water is everywhere. We believe that the answer to water scarcity should in part be found in nature. So our core idea is to look towards nature to find the solutions to some of the big problems that we as humanity face. And we'll get more into how we do that in practice. Today, Aquaporin is a company of around 80 people, and we pride ourselves of being a very diverse company and a very highly educated company, since we're a high technology company. So we have more than 21 nationalities working and currently speak more than 24 languages, not all of them at the same time, but there's a lot of different languages that people speak. We are, as I said, located in Denmark, and this is to show the scale of our operation, that we have upscaled membrane production and implemented it at full commercial scale. So we have membrane production capacity of more than 2 million square meters per year. So we have moved out of the lab and into full-scale commercial production. So where do we use our products, and what products do we have? If you look at the left here, you can see tap water reverse osmosis, you can see brackish water reverse osmosis, and seawater reverse osmosis. And these are the currently well-known membrane types in reverse osmosis. So we cover that full spectrum. And actually our first commercial product has been in the household market, so purifiers for your own home. And in India, that would be brands like Eureka Forbes or Kent or so forth. So this type of household purifiers, that's one application of our membranes. We are currently piloting brackish water and seawater RO, so high pressure membranes that can both be used for wastewater treatment, but also directly in seawater desalination, lowering the energy use and producing higher quality water. What we'll be speaking most about today is the second box called forward osmosis, which I said is a new membrane technology. We'll explain more in detail. And this membrane technology has applications very much in industrial and municipal wastewater and water reuse, but also in the food and beverages and medical device areas. But we'll focus first on industrial and municipal use of forward osmosis today. Aquaporin is a Danish company founded and headquartered in Copenhagen, Denmark, but we also have a presence in Singapore called Aquaporin Asia. We also have an office in the US, and we're also present in China. So we try to cover the world as best we can, but of course very often working with local partners. Then there's the last box, which is called Aquaporin Space Alliance. And that's because we wanted to highlight that actually our very first customer of aquaporin membranes was NASA in the US and ESA, European Space Agency in Europe, and they've actually been testing aquaporin membranes for reusing water in space. And obviously water in space is very, very expensive because you have to lift it up there with the rockets. So it's one of the places where there's the highest value placed on water reuse. And if NASA or ESA chooses to go to Mars, then we believe there's a fair chance that they will actually be using our technology to help get fresh water to the astronauts. Moving on to the core technology, I'll hand over to Jörg.
Yes. So Esben has been describing like what it's like how the company is built and how it has grown and how many people we are. But to like get there, we actually had to start from complete scratch, because there was no aquaporin membrane existing before we started working with it. And actually, like now we came all the way to commercializing it. And it's like how we are doing that. I'm going to go a bit more in detail now in the presentation. As some of you might know, like the aquaporin is a water channel that exists in all living cells. So that's the protein that's responsible for transporting water in and out of a cell. The discovery of it was actually happened quite late in science, actually in the 90s, where in 2003, Peter Egre, an American scientist, got awarded the Nobel Prize for the discovery of that channel. Before this discovery, we didn't really know how water is transported in and out of cells, and he proved it with the existence of this channel. And based on that discovery, our founders were thinking of, well, this protein, if it's that optimized for water transport only, why don't we use that as a tool to make water filtration in industry even more efficient and easier, because after all, nature does it best. If you now look at the channel in itself, you can see on the picture here that it's like it sits in a cell membrane. So like it is surrounded by a cell wall or a cell membrane, which is built up by lipids. So that's useful for stabilizing and actually like ensuring the stability and the capabilities of the protein. If you would imagine just putting a protein in a membrane, in a normal artificial membrane, and the chemistry there, that wouldn't really work. So like the first thing we had to do is to figure out how to actually stabilize that protein in its environment. How nature does it, it builds this lipid bilayer. So you have lipids which are basically hydrophilic and hydrophobic, and then they build together, two of them build a bilayer, which then wraps around the water channel, the protein, and stabilizes it. Lipids in itself, of course, as some organic substance, are prone to denature, the same as the protein. So if you want to think about an industrial water process, there are sometimes conditions that you wouldn't think a cell can withstand. And to mitigate that, we actually have developed a stabilization technique based on proteins, on polymers, sorry. So we take the protein, the aquaporin protein, and we put it in an assembly of polymers, and actually polymers that resemble this lipid bilayer or lipids. So you can have diblocks or triblocks where you then have the same like buildup. You have an hydrophobic and hydrophilic part, and they then can self-assemble into vesicular structures. And then the protein can sit within there. If you think about like the size of those vesicles, they can range from anything from 50 nanometers to 200 nanometers. So it's also very small compounds that we then have, but they are quite stable. Once the protein sits in this assembly, it is functional and can withstand quite some operating conditions. However, like also those vesicles would just be like floating away in a stream of water if we don't attach them or if we don't encapsulate them. So that's why we take those protein assemblies, like those vesicles with the active protein in there, and actually like trap them or encapsulate them in a TFC layer. If you're familiar with water and membrane technology, you know a TFC layer, that's the selective layer sitting on top of RO-type membranes. So you have a thin, something like a 200 nanometer thick layer that's built up of a polyamide, and that has already some good transport capabilities and rejection capabilities. And by incorporating the aquaporins, we can actually like enhance those. So it's like by using this TFC layer, which is a known technology, we already ensure that like the pH 1 to 13 or temperatures 4 to 70 degrees Celsius can be tolerated by this membrane and by the proteins without damaging them. So if you want to think about it, like the normal TFC membrane is of course permeable to water, and like most other or many other compounds or compounds are rejected, contaminants, but there's still some going through. What we do with the aquaporin membrane is then introducing a highway in the TFC layer, so like the proteins transport water faster than it takes to diffuse through a densely packed polyamide TFC. So we introduce like a highway, and since the proteins are highly selective for water only and nothing else can penetrate them, we also have a stream of cleaner water through, which in the end gives us the opportunity to have a cleaner stream, so a higher rejection or like a higher flux, or both together, depending on how we tweak the whole membrane layer and what we want to achieve and what we want to address. So it's like that is the overall aquaporin insight technology. Is introducing the biological selective component into an active membrane. If we now go into if you think about like a cell and a cell membrane and how transport works, the aquaporin is actually quite optimized for what's called osmotically driven processes or water transport. So in contrast to pressure driven, what we all know from RO, NF and other technologies, the forward osmosis is osmotically driven. So if we look at it in a way that we have a semi-permeable membrane, it's this blue construct here in the middle, that is separating two streams, where one we call the feed, that's the one with low osmotic pressure, and the other one is a draw solution, it's a solution with high osmotic pressure. So for example, just a high salt content. Here the membrane is semi-permeable, which means it only allows water transport, or mainly only allows water transport, and rejects like contaminants from the feed, but also keeps the salt in the draw solution, or like the active ingredient that makes the osmotic pressure. That way, nature wants to actually like equalize the difference between the two concentration differences, and it can only do so by water transport, since the ion transport is limited by the membrane. So we have a water transport going from our feed solution to our draw solution. If we look at it in a bit more technical drawing, then we have a feed solution that comes in, which is a diluted solution, comes out as a concentrate, whereas the draw solution comes in as a concentrate, gets then diluted by the clean water coming over from the feed solution, and gets diluted. Of course, in contrast to a pressure-driven process, we don't end up with clean water right away. However, we can have draw recovery systems that then separate the draw solution, so this high osmotic solution, from the feed solution, from the clean water that has been transported out of the feed solution, and then we end up with clean water, and our draw solution can just be re-looped into the process and do it all over again. So you have a continuous process of like producing your clean water. What is especially interesting in forward osmosis, when you compare it to reverse osmosis, there is certain process conditions that are completely different. Like in reverse osmosis, you have a hydraulic pressure, so everything you have in your wastewater is basically pressed against the membrane. It therefore creates a dense fouling layer, which often needs harsh cleaning steps. Of course, it has high rejection and high recovery, but it has also a shorter lifetime and like uses a lot of energy because you have to overcome the osmotic pressure that like works, the natural osmotic pressure between the clean solution and your concentrate that you produce. It's different in forward osmosis because here it's like, of course, no filtration goes without fouling. That's we don't have a no fouling process, but the fouling layer is less dense because you don't have an active full pressure that like presses your cake layer or your layer together. So it's a bit more loose, and that's why it's easier to clean. It fouls slower. It's easier to clean. It even has a higher rejection as reverse osmosis, especially when you put in aquaporins. And then, of course, you have you can go even to higher recoveries because your fouling is a bit delayed, and that's why you can also have then longer lifetime with the less cleaning. And of course, you have a lowered energy consumption if you run the forward osmosis process only. Of course, if you have to like couple it with a draw recovery process, then of course energy might be the same, but you end up with a process that is lower in OPEX in the overall because you have less membrane exchange and a cleaner water product usually. So with what solutions do we actually like tackle the whole thing? Forward osmosis is the big advantage, as I said, as there's no high pressure. So that's why we can introduce the hollow fiber technology, where we have a high packing density, so a very compact and lightweight design for a lot of packing a lot of membrane area. Of course, we have the aquaporins in there, which gives us the high rejection, and with a high membrane area and the combined with the forward osmosis process, we also end up with a high recovery, which gives us a high efficiency. So we can, on a small footprint, concentrate solutions quite easily and quite to a high degree. We currently have 3 different products on the line, and just to point out how much you can pack in a hollow fiber module, like the hollow fiber 2, for example, that you see in the middle here, it's about that size. But it has space of 2.3 square meters active area. You can't do that with a Spiral 1 module, and that's why the hollow fiber technology is very good for forward osmosis, because it can pack a lot of area in a small footprint. However, like if you want to have, of course, as you see here, the inner diameter of those fibers is quite small with 0.2 millimeters. So if you want to have something more viscous or with a TSS content, so like suspended solids, you might want to change to something that has a bit larger in the diameter. And that's why we also have, and here again, as Esben pointed out before, we are open to work with partners. Here actually with Berghoff membranes from Germany, we developed a tubular module that has our coating on top. As the base is from Berghoff, our coating on top, and is ideally then for something like fruit juices, or where you have like high viscosity that you need to treat. If we now look at just some examples to give you an impression of what the Aquaporin Insight technology can do in forward osmosis, we have just some examples from the different industrial water industry. We have from lentil or from semiconductor here some examples of contaminants, where we have a rejection of copper, iron, nickel, and fluoride of over 99 point, well, the lowest at 0.5%. So actually, like almost rejecting everything that comes our way. Of course, boron compound prone, that is known to be hard to reject. We even got at 94% water recovery, so removing 94% out of a feed solution, we still have an 87% rejection for boron, which is to our knowledge like unrivaled in membrane processes. And that can even be like increased when we do a pH adjustment if needed. But of course, you want to adjust so little as possible because you want to keep your process as a low key or as undisturbed as possible. We now look at another thing that's important in FO is the performance efficiency. Here you look at the water flux and what we call the specific solute flux. The specific solute flux is made up of water flux and a reverse salt flux. The reverse salt flux is a phenomenon that's typical for forward osmosis processes. We don't have a membrane that's 100% semi-permeable, 100% selective for water only. So you always have a certain background noise or a certain diffusion of ions going through because there is an ion imbalance in between the feed and draw solution. So you have a diffusion of ions going from one side to the other. That is, some ions, as you've seen before in boron and so on, like go through the membrane in forward mode, like with the permeate, but there's also ions of the draw solution diffusing back into the feed solution. And that, of course, has influence on your process, how much that is. So you want to keep that back diffusion or this reverse salt flux to as low as possible, because it minimizes your use of draw solution, replenishing, and it also keeps your feed solution free of that salt or whatever you use in your draw. The specific solute flux on the right here then says like how many grams of salt do we lose per produced liter of water. And with the membranes that we use, we usually have an 0.1 or even lower grams per produced liter. So you lose 0.1 gram of your draw solution per produced liter of water. And you can also see the higher your osmotic driving force, this one, your salt draw solution concentration, the higher your water flux. However, that's not necessarily linear because there's effects like the internal concentration polarization playing into that as well. But I'm not going further into detail on that, but there's some very interesting papers being discussing that phenomenon. Now if it comes like what can we actually do with that technology, we actually have two fields that we look into here at Aquaporin and together with our collaborators and customers. There's one side is industrial water and the other is the food and beverage. Let's take a closer look at the industrial first. So basically you have lots of different industries. It's not limited to any one industry, but you have lots of industry where you need to minimize your waste. You want to reuse water or you want to simplify your effluent treatment. And that you can actually do with our with the FO technology, also then reducing the installation size or improve logistics in that. And all those together then of course will increase your profitability or sometimes even like or just your sustainability and your green footprint. But that is also a very important item to consider these days, especially if you can show that in a responsible manner, that you like responsibly manage the water resources, as pointed out in the introduction here, the limited water resources that we have on our blue planet. If we now look into the efficiency of water treatment of industrial water, of course we have problems with contaminated groundwater and rivers, and that all over the world. Basically, wherever you have industry, you will have a challenge with wastewater, and there we trying to like help the customers or the countries in itself to like clean up or reuse some of the waters. I want to introduce like two examples that we had. Here we work together actually with a customer, but we have done it so far only in lab scale. When you see like the current process, they have the factory, they pump and process water, it goes to a wastewater tank, and then they can discharge it to the sewer. However, the sewer discharge is something that is very much limited, and it gets more and more limited the further we go and the further they grow as well. And of course, it's not as responsible to like just have water going through and then like have somebody else take care of the problem. So what we want to do is actually we can take the processed water in the factory after it has been used in all the processes. We can extract water and reuse it, and then not discharge to a sewer, but you can actually have a very small effluent that you can truck away. And if the application allows, there's usually or there is sometimes the possibility of providing that effluent, because it's concentrated, to what is it, a biogas plant, and actually use the material in there to produce energy. Here, for example, we had a wool processing plant, and we used forward osmosis to reduce the effluent volume and produce clean water on site. We could recover up to 98% of the water from the effluent. So you have to like imagine that if you had a cubic meter of water that came out, then before, now you only have, well, 20 liters coming in the end. So that's a huge change.
It's going from a container to a bucket.
Exactly. And there, of course, you have savings on the raw water sourcing, which it makes less stress on the environment, because you don't have to pump out a river, you don't have to pump it out of the groundwater or anything. So it's a more sustainable solution. And of course, you have your effluent volume reduced by quite a lot in the end. The second one is actually where it already happened, that the factory used to be able to produce their wastewater and then just discharge it to the sewer, to a centralized treatment plant. Suddenly that's not allowed anymore, because either the treatment plant is too small, or the municipality says, well, we can't treat your wastewater because there is compounds in there that we don't want in our treatment anymore. So then, of course, these companies or these examples have suddenly a problem on their hands. What is usually being done? What's the normal thing you can have? And what they did, they have the equalization tank. Because of space, they couldn't really do any pre-treatment. They used an UFRO, then an evaporator, and then they truck it away. Problem there was, well, they didn't have a big footprint left, so they couldn't install all the necessary pre-treatment. That's why UFRO failed in their pilot tests, because of fouling and clogging and whatever else happened. There's actually quite a mix of factors that influence that. But they still have to minimize their wastewater, because they don't want to put it all the water that comes from an equalization tank to an evaporator, because that makes your evaporator big, that makes your energy consumption even bigger. So what we do is to put in a forward osmosis process and reduce the volume that comes to an evaporator, and at the same time have clean water again reused in the factory. So here in that example, we actually went up to 70% water reuse, which makes it 70% less volume that has to be treated by an evaporator. That, of course, has an influence on how big your evaporator needs to be, how much money you have to invest there, and of course, how much energy you're going to use to do that. So they could, they can decrease their footprint, and of course, the capex, opex that they need for other treatments. And that's also here, forgot to mention that, a textile effluent from a nylon dyeing that came in here. So that is two examples, and then of course one more example, which is a bit more out there, you could say, in preparation for further Moon and Mars bases, or wherever we want to go at some point. Water is a very important factor there, and as soon as we go out from the lower Earth orbit, where ISS is, to beyond that, water resupply is not just possible in a week's notice. If you think of Moon or even Mars, it takes a bit to get there. So if you want to have a permanent or semi-permanent residency there, you need to be able to reuse a lot of water. And here NASA has actually at their research center in California installed what they call a sustainability base, where they try out all kinds of techniques, not only for water, but also other technologies that they might be able to use for a base that has to be coming up in space. Here we actually, that example, we treat gray water. So gray water is all the water that comes from a building that's not from the toilets. So you have sinks, showers, well, your kitchen kind of, and like all that water is pre-filtered and like, or it's basically collected in a tank, which is for that building only like 1 cubic meter per week. But it is an ideal size for us to try what's possible. And here actually NASA installed a solution that can reach up to 85% water recovery. It treats the one cubic meter in 8 hours. So like the process only has to be run once a week, and then you have 85% of your water that you can reuse. And the other water can then be treated either in evaporator or other technologies. So you can also even recover more there. They actually want to run it with as little maintenance as possible, because as you can imagine, on a moon base, you don't have cleaning solutions or other water rinsing supplies that you can just employ. So they basically just running the process as it is, shutting down the modules in between without further treatment. And for now, it has been running for almost a year there with a consistent result, and they'll keep it running that way. So that's actually a solution where, even though you don't have the optimized like water flux that you want in an industrial process, you have a stable water flux with low or no fouling that is then actually transporting water the whole time. And that's something that is highly valued by those NASA engineers. So now to like go a bit more in the other way, away from wastewater to actually like valuables and concentration there, Esben will take you a bit further into the food and beverage examples that we have.
Yeah, I think we just have 5-7 more minutes before we round off and take any questions. So let's look a little bit into food and beverages, which is of course also a very big industry, and not the least in India. If you look at FO as applied, forward osmosis as applied in food and beverages, then it's about product concentrations. You can concentrate your product while retaining aromas, nutrients, flavors, so make a natural product just without the water. You can make super concentrates, so concentrates to even higher level than you otherwise could, especially with filtration solutions, with an improved quality. And that can actually both lead to better logistics costs. It can also lead to lower processing costs, and then you can even make new and improved products with better taste and flavor profiles. So this is a very interesting value proposition. It all comes from basically a favorable comparison to either traditional filtration or to evaporation. If you use other filtration techniques, you will lose more of the aromas and flavors, and you will not be able to concentrate to as high a degree as you can with forward osmosis. Whereas if you use evaporators to concentrate, then you will have very high, especially operational expenses for energy, and you will basically be cooking your product since you're evaporating it, and that of course deteriorates the flavor profile. So let me briefly show you 2 different case studies. The first is on coconut water, which fresh coconut water is a very specific taste that is highly valued by consumers. So either you ship it at the full volume, or if you concentrate it, then you have to accept that you change the flavor profile. At the same time, coconut flavor is also desirable for a lot of as an added flavor for mixing drinks where you cannot use the full coconut water. So there's a desire to have a concentrate that retains the fresh flavor of coconuts. So what we did here is to use forward osmosis to concentrate from 4 brix concentration of natural or 3.5 brix of natural occurring coconut water, and all the way up to 65 brix, which is really into where you need an evaporator to go otherwise. So 18 times concentration, and we could do that while retaining the natural flavor profile. And this was done with a client, a customer, who was very impressed with the results. That was one example. Another example is coffee. Coffee is, of course, both fresh brewed coffee. It's also instant coffee, so freeze-dried coffee, and it's also mixed drinks coffee, so coffee with milk, coffee with all sorts of other additives or flavors. So it's a big and important product, and again, it's one where the aromas and flavors are valued very, very highly. I think most of us know the difference between a freshly brewed cup of coffee and instant coffee. And instant coffee, that's basically the taste of boiled coffee, coffee that's been boiled until all the flavors have gone off or changed. So this is a quick lab scale example, going from 2.5 bricks up to 96% water recovery, and ending up at this very, very concentrated coffee substance. And again, the only thing you see going into this bottle is two hoses for circulation, and that then goes through the membrane module. So there's no high pressure pumping or anything like that, just a simple circulation pump, and then the power comes from the draw solution. And coffee is a place where there's a lot of experimentation and innovation in terms of new products and new flavor profiles and different ways of preparing coffee. So we view this as a very attractive application that we have high expectations for. So since this was primarily a water seminar series, we didn't want to spend too much time on the food side, but that was a quick taster. So basically, to round off, I wanted to put up this page, which is showing different pilots and small operational facilities around the world, from Canada to US to India to Denmark, showing the Aquaporin inside technology working every day. So the next stage we're at is now we're working with innovative and forward-looking system integrators and end users, mainly in the industrial space, and also in public partnerships and with research institutions, to prove the technology at the first scale of industrial installations. So for example, 100 to 500 cubic meters per day capacities, and then moving on from there. So that's the current stage we're at. And as you saw here from the examples, we have done a lot of work in the textile industry, and actually India is very much at the forefront of forward osmosis technology, and that's because of the very forward-looking regulations for zero liquid discharge being implemented in India, especially for the power industries, textiles, distilleries, pharma, chemicals. This very bold move by the Indian government to reduce wastewater discharge and to implement zero liquid discharge has really created an innovative environment where the Indian water sector is really looking for new solutions, and also for better ways of doing minimal liquid discharge or zero liquid discharge than the traditional evaporation. So there's a lot of things going on in forward osmosis in India this very moment. So we find that to be very exciting. And with that, we will round off our presentation. I hope you found it interesting. We're very happy that you gave us the time to listen. And if there are any questions, we'd be, of course, very, very happy to answer them. Thank you very much.
Thank you.
Thank you for the nice, lucid presentation. In fact, there are several questions. There are 30 questions now. And we may not be in a position to take all the questions. So I'm going to sort of condense some of these questions and present them to you, as many as we can take in the next 15-20 minutes or so. Obviously, when anybody talks about water, everyone wants to know the cost. So let me start from there. First question is that what would be the cost per cubic meter, and how do you compare that with available technologies in the context of domestic RO, industrial RO, wastewater treatment?
I can pitch in on that. And of course, it's a very, very good question, because there is no such thing as the golden arrow or the silver bullet in the water technology. Everything has its place. Forward osmosis lives in the space between ultrafiltration and reverse osmosis on one end, and evaporation on the other end. So I would say if you have a well-running reverse osmosis system, excellent, then you don't need to worry about forward osmosis. It's a highly optimized technology, costs are very low, excellent. But if you're in a space where you cannot use your reverse osmosis due to fouling or due to poor permeate quality, then you start thinking about forward osmosis. On the other end, for evaporation, in general, forward osmosis can reduce the load on evaporators and save you money. So we believe we basically have a business case everywhere there is a wastewater evaporator. So that's the space we're in. Of course, it's dependent on the discharge cost. It's dependent on the energy cost and all that, but it's within this space. So I hope that gives an idea of the answer.
Very nice. So wherever there is some kind of significant clogging, maintenance-related issues, wherever there is RO is likely to fail or has failed continuously, there is a business case. And will that business case be economical is the next question.
The best case I can give is we recently worked with a client in India, a textile plant, who was looking to install an evaporator for the discharge to achieve zero liquid discharge. They then did the comparison of installing an FO unit and then with a reduced evaporator, and this client arrived at a return on investment of 7 months. Which is very, very short. So yes, we believe it is economical. Of course, not in every case, but in many cases, we believe there's a good place for it.
Yes, I am aware of this case, and so it's very nice. You talked about 2% reject, and reject is a very big problem in RO, and many, India has regulations on it. And more concerns are coming up. Meaning that with reduced energy, obviously there is a big, possibility. What would be the sort of theoretical limit of energy utilization in FO, combining all of these processes together, recovery, everything together?
I'm not sure I get it.
So the theoretical limit on energy use per cubic meter, is that the question?
Yes. If I were to take it to, let us say, 2% reject, that is great for any industrial process. Now, if you combine that with energy saving, it makes a great proposal. So what would be the limit in energy is the question.
Well, there's several things we have to consider there first. We had one example here where we had 2% reject only. That is very application dependent in the first place. But let's say we can achieve that. Then it's of course a question of what draw solution you have and what draw solution recovery you have, because that is where your energy is mainly used. FO in itself is just recirculation pumps. They don't use very much energy. So it all depends on your recovery system. And of course, if you have to have a reverse osmosis or a high pressure reverse osmosis recovery, then your energy saving in the overall process might not be as significant as when you only use a FO process, but you have other OPEX savings on pre-treatment, on especially evaporation. And if you go to take a chunk away of the evaporator, so if you say we have only 2% reject instead of, I don't know, 40% reject that you have with an RO system, if you only run that, then your energy saving goes directly from your evaporator. But the minimum energy you need to put in is usually the energy you need to put in to recover your draw solution, whatever concentration that will be.
So that takes to this question as to what is the draw water, draw solution recovery. What is the process used, and what is the limit that is possible today in terms of energy utilization?
Yeah, there's several. For us, there's two cases. There's some cases where the benefit of FO comes from the full operation of as you have been limiting pre-treatment and going to higher concentrations, and then there's the other cases where you need to optimize, to really hardcore optimize for energy use. For example, if you want to compete in desalination, where that's the only thing that really matters, that's the overall energy use. And for the second case, where it really has to thermodynamically be optimized, the full process, then you need a highly specialized draw recovery technology. And the reason why we're not being very concrete right now is that those specialized draw techniques, that's not something we provide. We provide the membrane, and then we build it into sort of the simple systems with high pressure RO or something like that. But we cannot answer specifically for the fully optimized system. But I will say that both in at least 2 places in the US and 2 or 3 places in the Middle East, there are big demonstration facilities running to show that forward osmosis with the right draw recovery can improve energy use in seawater desalination. So we believe there is also a market for this, but it's not something we are proving ourselves in pilots.
This is where many experts comment on that the success of RO versus FO will depend upon how you can recirculate, recover the draw solution. And that obviously is another debate, and I know that you are not working on that, and so there is something that we have to direct that question to those who are working on a draw solution. But that is an important aspect that you flagged. That is very nice.
But if I can I make one comment there?
Yeah, sure.
It is that forward osmosis has been promoted for many years and is investigated for many years, and the main interest has been exactly in the thermodynamics in reaching the optimum kilowatt hours per cubic meter. What we're actually saying is that's very good, and we believe that there's a case there, but there's a lot of benefits of FO also without going for that full optimization. So there's a lot of places where even with traditional RO as recovery, you can get a lot of benefits. For example, via the higher rejections and the lower fouling propensity. So that's actually where we are ourselves focusing.
I know, I understand. It is not really that we are really not comparing FO versus RO now. We are talking about FO with aquaporin inside, and this is also something different. So I do fully understand that. But then, for the benefit of the viewers, and it is important to clarify certain things, I need to present these questions to you. Now, in terms of the footprint of RO versus FO, for a given unit, let us say, unit volume of treated water, how do you compare this?
Well, it's like in footprint, there's of course the first the membrane the area that you need, or basically the membrane area. As I've shown, we can pack a lot of more membrane area per cubic meter of space than RO can. However, RO membranes have the higher flux through usually. But that's why with like where your RO process, as Esben said, where your RO process works fine, there's no need to install an FO solution. However, if you have an RO process that needs, I don't know, 3 or more stages of an RO, which then actually also translate into a certain footprint, right? Then you might want to think about if there's other possibilities you can use, for example, an FO. And these FO membranes, based on the hollow fibers, can be quite densely packed and stacked. So in that sense, I would say there's an advantage of the FO, and especially because you don't need big stainless steel piping and everything for it, because FO works on pressure-less application. So like your whole system can be constructed completely different than your high-pressure RO system. Also, your pumps are way smaller. So that all plays into like the footprint advantage.
So if you compare only the membrane area, FO versus RO, then you need more membrane area and it will take up more space.
Yeah.
But if you look at the full system, then the picture is more complicated.
And can you share some ideas about the capital cost for a full blown up system?
What's your best example?
That depends. I don't have one right here, but if there's a certain application somebody thinks about, then we don't have a full application installed so far. That's the biggest challenge.
Give an idea about, let us say, 100 kiloliters per day or 200 kiloliter per day. Typical small scale miniature industries.
Yeah, for the pure FO part of that installation, the FO rack will be in the I guess a couple of tens of $1,000s, $10,000-$20,000. But then, but that's of course a small part of the full installation. So I cannot give a number with also withdrawal recovery and with the full pumps and piping.
So may I say that for the benefit of the viewers, that it is important to work with you for a given problem if the problem is sufficiently challenging.
Yeah.
Industrially, if it is sufficiently challenging and if RO cannot be the right solution, one can work with industry. And there is an Indian example wherein you see that the costs are competitive.
Yes.
Am I making the right statement?
Yes, and also that we work with system integrators and solution providers in all geographies to actually do the full quote and do the full installation.
Can you comment on how long can the membrane be used and how do you dispose it off and things of this kind?
Mm-hmm. So in general, of course, membrane lifetime depends on feed and pre-treatment, of course, but we see at least the same lifetimes as for RO membranes. So we have no limits in lifetime due to our technology that we put in, and because of the lower fouling of FO, we will generally see longer lifetimes. So in normal, fairly small scale industrial applications, we would expect maybe 2 years, for example. But if it's bad feed or not enough pre-treatment, it could be 6 months, just like with reverse osmosis. And we believe for highly optimized, for example, desalination with very careful pre-treatment and chemical adjustments, we could be looking at 5 years. So that's those sort of ranges, which are the same type of ranges you see for reverse osmosis.
So as far as the disposal is concerned, you don't see any issue?
The disposal is, well, the membrane is pretty much, except from the protein, is pretty much built up as like RO membranes are. So like the disposal of RO membranes also is right now, unfortunately, still either landfill or incineration, and there is no perfect recycling or anything yet for those membranes. And unfortunately, that's the same for ours. We use the same chemistry on it, which is playing also into the point, and like what Esben had, it's like you can compare it to traditional membranes because it's a TFC layer that has been working on our own membranes for years and years, and so it's comparable to that in the chemistry wise.
I'll say that that's a subject that's very close to our hearts. We have not solved the full life cycle issue of membranes, just like the industry in general have not. As soon as we start producing higher volumes, then that's something we will dedicate more time to. But we have to be successful in really getting the process implemented first. But we will very much welcome collaborations or suggestions on this point.
Yes.
So while I started, we had 30 questions and now we are at 52 questions. So obviously it will be difficult to answer all of them. So I have a couple of questions to ask you with regard to the future. One is it FOB, can it be used for gas separation? Are there some directions in that? And you talked about food and beverages. How about dialysis and biological applications? So what do you see as future, as many different possibilities?
I'll leave the gas separation for you.
Well, the gas separation is one thing. With our technology, we are not going into gas separation for now, since we're using a water channel. Like the Aquaporin is made for water, so like that's what we concentrate on, and like and at some point we want to, if you look in the future, have only water channels transporting water. So that's what we go in first. As for osmosis for gas separation, to be honest, if you can make a membrane that's only transporting one type of gas, in principle, it's possible to make the same principle for gas separation, because it's always a matter of concentration differences creating a driving force. For us, it's the membrane limits all other ions, lets water through. If you then have some gases that you can handle the same way, theoretically, yes, but it's not anything I'll probably will ever go into.
And if you look,
how about biology?
Yeah, if you look at other applications, so there's a couple of anything there's a concentration where you remove water. That's something we are interested in looking at. Examples are lithium extraction, for example, which is an emerging area, concentrating lithium. That could be an application. All over the pharma space, pharma biologicals, concentrating after fermentation. That could be a forward osmosis application, both because they're fragile and also because you can be using a lot of energy there. There's all sorts of other valuables like dye concentrations, or so there's a lot of applications like that. And if you get a little bit more sort of thinking outside of the box, then I would like to take a look at the improving sensibility of biological testing. If you're testing for viruses, for example, you have a problem of what's your detection limit, and if you can remove the water, then you can improve your detection limit for viruses. And it's very hard to do this without either destroying the virus or having it absorb into your filter and disappear. So that's another place that I think could be interesting to look at, also given the current global agenda, I would say.
And if we there's one more thing, if we look futuristic, and actually something we already have some collaborations with academia partners together, is we know how to stabilize a transmembrane protein, which is the Aquaporin protein. But that's not the only protein that sits in a cell membrane. There's others, let's say ion channels or something. We could also stabilize those. And if you can stabilize those, then you can make an ion selective membrane. And to whatever ion like your ion channel can transport. It's nothing that is on the product pipeline right now, but academia is working on it, and we actually do have a collaboration with some that look into these cases, because once you stabilize one transmembrane protein, you can do it with others as well.
I don't want to go more into the technology, because of course there are a lot of technology protection and things like that. But then people would like to know, what we are seeing behind this picture, are you really taking aquaporins from leaves?
Not right now, but not for the big scale production, but we are taking it from leaves as well, from in more exploratory or cases.
But for low cost production efficiency, we produce by fermentation, and that has been a big part of our core technology, producing aquaporins at scale at low cost.
Mm-hmm.
Well, I would stop by asking one more question, and you know, there are a lot of youngsters watching this presentation, and you mentioned that 100 people were trained, and you are open, and you have been having industrial collaboration, academic collaborations, etc. Now, obviously, there are a lot more to be done. Do you think that young people have a future with aquaporins in terms of technology development, science?
Yes.
Yes.
That's a simple answer. I can only say yes, because it's like as I can point out from my own example, I started here writing my master's thesis with Aquaporin, and even went through the Ph.D. program together with Aquaporin, and I'm still here. And at that point, I would say I was still young when I started. From the 100 people that like came through here, I think it's like, of course, we can't keep everyone, but we still have a couple of those people that have done master, bachelor, or other theses with us, and that are still around. They still work for us. Even others that have worked for us a bit, then went out into other companies.